We are coming to our next presentation. We already heard about the testing field for autonomous driving in Karlsruhe, but the city of Ulm is a very interesting test site for automated vehicle, as well as one of our hotspots for this topic in Baden-Württemberg. So we are very glad to give a warm welcome to Dr. Michael Buchholz from the University of Ulm. You're working for the Institute of Measurement, Control and Microtechnology since 2009, I think. So more than a decade already before you received your diploma and your doctoral degree from the Faculty of Electrical Engineering and Information Technology at the Karlsruhe University. So the same as I said to Alexander, we met a lot digitally in the last year, so it's really good to see you here, and I'm looking forward to your presentation and discuss with you later on in the panel discussion. Michael, the floor is yours. Thank you.
Thanks, Wolfgang, for the warm welcome, and welcome to all of you to my presentation on supporting on how intelligent infrastructure can support connected automated vehicles. What I'm presenting here is more or less the result and ongoing work which we do in several research projects. But to give you a little spot on the background, the Institute of Measurement, Control and Microtechnology, our director is Professor Klaus Dietmeier, and he founded the group of automated driving driver assistance systems about 20 years ago. At the moment, more than 20 researchers are working only in the field of automated and connected driving, and additionally many students. We are a partner in several public funded projects, for example, the U-Shift project, which Tjalk presented just in the presentation before, on a state of Baden-Württemberg level, but also in federal funded projects like the Unicar Agile, the Lucas project, or on a European level, the ICT for Car project. In addition, we have several research contracts with OEMs and suppliers. On a methodology side, we focus on information fusion, multi-object tracking and localization, and also machine learning for classification and scene understanding, just to mention 3 spots where we really focus our work. Overall, we work on the whole chain of automated and connected driving at our institute. But now coming to the main topic of the talk, the connected automated vehicles and the infrastructure supporting them. I personally led the work package in the ICT for Car project, where you can see the partners on the right side, and the work package on the high-level system architecture. In this project, we developed an architecture which is able to integrate several different communication technologies. In this project, we focused on the LTE 5G mobile communication, which you can see on the right side of the architecture picture, and the ITSG5, or dedicated short-range communication, DSRC, as you can see on the left side. And then we have sensors in the infrastructure, for example, which are either connected to the mobile network, like on the right side, or directly have an ITSG5 RSU, like shown on the left side. And to allow for very low latencies, because real-time applications for automated driving don't allow for a long transportation and delays in mobile communication or even wired communications, you have so-called mobile edge computing servers, either on the base station of the mobile network or directly at the roadside units of the ITSG5 network. And also the sensors can surely be connected to both, and we call that a hybrid communication. For sure, we also have some services which are not latency critical. So these can be in the cloud, like back-end services of OEMs, different service providers like map, weather, or whatever. And this can be provided over the internet to those vehicles. And you see the vehicles, which are kind of like agents or clients in that system from an infrastructure point of view or communication point of view, which can either connect via ITSG5 or via 5G or LTE or both, so they can use the hybrid communication. But now coming more in detail to the vehicle. So what are the functional modules of a connected automated vehicle? For sure, an automated vehicle needs sensors to perceive the objects and its surroundings. We need a very precise HD map and a differential GPS transceiver to know where we are. Using the map and the GPS and also sensor data, we can have a very precise localization with respect to that map. And the sensors detect all the moving objects around us, so the other vehicles, the pedestrians, the bicyclists, and all that. And this is all together summed up in the so-called environment model. Based on that model, the vehicle has to understand what's going on around it and then has to decide what to do to reach its goal where it wants to drive. So it has to plan its behavior and then plan a trajectory. That's the direct way it's going to drive in the next few seconds. And then the vehicle has to be controlled to follow that trajectory. So now how can intelligent infrastructure support that vehicle? You can have infrastructure sensors, for example, as a first step, which also provide an environment model from their view on the scene, for example, at a crossing, a junction. And then this environment model can be sent to the vehicle, but then in the vehicle, you have to be sure that this data is valid, that it's reliable. So what you normally would have is some kind of reliability check, which needs to check the reliability on very few samples. So normal statistics on large numbers don't work here. I want to give you a short, more detailed example on exactly that application, which was part of the MacView project, which we finished last summer. We call that the virtual mirror. It was performed on our test site in Ulm, where we have intelligent infrastructure sensors on public roads and in the suburban area of the city of Ulm at a T-junction, which has no traffic lights. The driving task for the autonomous vehicle, which you see in red, is to drive onto the junction and merge either right or left on this T-junction and yielding the right-of-way of the priority road. But as you can already see on the right side, buildings or other infrastructure elements could occlude the view on the main road for the automated vehicles. So from its own onboard sensors field of view, it cannot know if there's a vehicle behind that building or not. So the red area is not visible for the vehicle at the moment. So what it normally would have to do at this junction would be to drive at the yield line, stop, sense the environment, and then start again, which is not very efficient for the other traffic, for example, and also for the energy consumption. To give you a more detailed view on how this looks at the intersection, I have a video from one of our test vehicles. When we start this video, you see from a cam what the sensors of the vehicle would also see. So you see the building on the left side, and we are not almost there at the junction, but we can see through the building. And what we want to have is that infrastructure sensors open that field like if the building would not be there. So that would be our goal that we want to achieve with our infrastructure sensors. So the solution is to use infrastructure sensors and to extend with them the field of view of the automated vehicles, which are connected to those sensors. Then an environment model in the infrastructure can extend the field of view and makes the occluded road users visible to the connected automated vehicle. And then the vehicle can already make its decision long before it can sense the objects itself. So what was the infrastructure setup for this field test which we performed last year in Ulm? We have sensors with sensor processing units. In detail, we use cameras and LiDAR sensors at lamp poles, and the sensor processing unit already did a pre-processing. So they detected the objects from the sensor data and only sent the object data via mobile network to a MAX server. The LTE 5G mobile network was a test network by our partner Nokia, which performed with very low latencies and features a mobile edge computing server. And all the SPUs and also the vehicles connect to that server and can receive the environment model, which is calculated on that MEX server. This model fuses and tracks all the objects from the received from the sensor processing units, but also makes a prediction of how the scene will probably evolve in the next few seconds. This makes sense because a vehicle only can make a prediction which is very general because it has to work on any junction in the world. But for the infrastructure, this is can be a very tailored prediction which is perfectly fits the behavior of the other vehicles at this intersection. And the prediction allows, for example, to account for latencies which occur, or also to predict how the movement will be so that we can have a predictive planning of our own behavior. Now you will see a video. On the left side, you see the front cam of the connected automated vehicle. And on the right side, you see in green the road boundaries. In blue, the boxes are the objects from the environment model from the infrastructure. And the red dots are the LiDAR sensor points from the vehicle. And I will start the video, and you will now see that the vehicle, with that information from the MEX server, with this environment, it can directly merge behind the vehicle onto the main road and not anyhow braking. So this is very energy efficient and also efficient for the traffic flow at this intersection. But is that already anything what we can do with this infrastructure? Is this the only intelligence to perceive objects from installed sensors? No. In ongoing works, we work on also integrate road users' data, the objects their own positions, and also the objects they may retrieve. And we also integrate vulnerable road users like pedestrians or bicyclists using smartphone, which are connected to the MEX server. And then the server can also work on cooperative maneuver planning. So it can provide some suggestions to the vehicle how to behave at this intersection, which then also has to be checked for reliability and then can be driven by the automated vehicle connected. Is it already all, or is there something which is beyond that? You see a wide free area in the right, and for sure the next step could also be that we have also trajectory planning in the infrastructure, and the vehicle only checks if this trajectory is available. This is more or less the managed automated driving Thiago was talking about in the talk before, and this completely adds up to this idea. With that, I want to thank you for your attention. If you have any more questions, please feel free to contact me, and I would also like to thank our funding agencies, the Federal Ministry of Economic Affairs and also the European Commission, which funded those works in the projects MacView, Lucas, and ICT for CART. Thank you.
Thank you very much, Dr. Michael Buchholz from the University of Ulm. As we have 2 minutes left, I have 1 or 2 questions to discuss with you. So you presented a lot of interesting aspects concerning infrastructure. If we just think of the future transportation system, so I would assume that brings some. If we look at the project partners in your project, so this brings some new kind of actors in the mobility sector, which were not in the mobility sector in the past.
Right, totally right. For example, I said our test network is operated by Nokia, so we have all the many partners which we have in those projects are from the communication area. So we have OEMs and suppliers like Bosch and Daimler or BMW in those projects, but on the other hand, we also have Nokia and the typical traffic infrastructure suppliers like Swarco, for example, which are partners in those projects, and they more and more work closely together now for getting that infrastructure for the intelligent driving running. And this is not only for the automated vehicle itself, but as you said, also for intelligent transportation systems. So having a more global look on the overall systems to get the for example, for traffic efficiency also.
As we have very intense discussion about digital infrastructure in Germany, is 5G or in future 6G, is it really crucial to have intelligent transportation in the future?
It depends on which task you want to have. If you say the vehicle should always perform each situation on its own, then you wouldn't need that. But if you want to have services like I presented with the environment model, you would need at least a 5G with a low latency possibilities, which only 5G offers, so that you really have very low transport delays of the information between the sensors, the MAC server, and also the vehicles. Because otherwise, if you have to transport that via LTE to some cloud server, the information would be too old, and the vehicle could not rely on that.
So still a lot of work to do.
Yeah.
Yeah, thank you for now, Michael. We will see each other again in the panel discussion.
Thank you.
So thank you very much for the interesting presentation.